So good afternoon, everybody. For those of you who don't know who I am Jane Fitzpatrick, and I'm the COO of the Australian National Fabrication Facility. I would like to welcome you all to our first completely online webinar. It was to be a joint in-person and webcast, but due to the circumstances that I'm sure you are all aware of, we decided to go fully online for this particular seminar. So thank you all for jumping online and helping us test this format out for the future. I will say that this seminar is being recorded, so please be aware of that when we do get to the end of the question and answer section. So, to the seminar itself. This is a seminar to start talking about simulation and how simulation fits within the capabilities of the Australian National Fabrication Facility. Obviously, many of you out there make things on a regular basis. But what simulation allows you to do is actually validate those designs that you're looking to make quickly and effectively before you actually put them into practice. This can save you time, effort, and money, which is always a wonderful thing when you're looking at research. So the reason we have been able to roll out this particular service is the person you will see on your screen very shortly, and that's Moein from our South Australia node. He's been doing this for a number of years at South Australia, and very recently we've decided that his skills are wasted just being given to the South Australians, so we want to roll them out nationally. So this seminar is about him telling you what simulation can do for you and some case studies as to what it has done for other researchers in South Australia and elsewhere up to now. Obviously, this is part of a capability that ANFF believes will be beneficial to lots of our users around the country, and it also fits that ANFF is not about giving you capabilities in your locality, but giving you access to these capabilities. So having Moein in South Australia does not mean that you don't have access to him. He's there, he can do everything you need him to do, and he's just on the end of the phone or email. So the platform we're going to use today, as you've all logged into, is Zoom Webinar. It has a couple of functions that I'm just going to run through quickly now so that everyone's aware of how this is going to work. I will be switching over to give Moein control, and he will present his seminar to you. He will stop at natural breaks within the presentation and check the Q&A list at the bottom of your screen. So if you look at your screen, with your cursor down the bottom, you will see a Q&A button. If you press that, it will allow you to type in a question. That question will then go to the system, and during the breaks in the seminar, Moein will look at those questions and answer them as he goes. At the end of the seminar, we can then go to a more verbal question and answer session. And as you can see it down the bottom of your screens, you'll have a raise hand. So when we go to that verbal question and answer session, please just click the raise hand and we will go through those, and you can ask we will unmute your microphone and you'll be able to ask questions that way. So I won't ask if anybody has any questions right now. What we'll do is we'll just launch straight into this seminar, and I will pass this over to Moein, who will give us some really great information on how simulation should be a very vital part of the start of any fabrication process.
If you'd like to share your screen.
Yes.
There we go, and take it away.
So, can you see my screen?
Yes, we can.
All right. Good afternoon, everyone, and thanks, Jane, for the nice introduction. My name is Moein from South Australia node of Australian National Fabrication Facility, and I'm going to briefly talk about the tool and the technology that can be used with your design or within your manufacturing process to inspire your idea at research and innovation and help you to discover the better design faster. And that's simulation. So I would like to start with some statistics. These statistics published by Aberdeen Group in UK, which monitors the performance of design and engineering organization worldwide. So it's been reported that 87% of best-in-class organization use the simulation in this process. So as an example of best-in-class organization, I can mention the big names like BMW, Ford, and Audi in automotive industry, Airbus, Boeing in aerospace engineering, even General Electric, Philips, and Samsung in mechanical or industrial engineering, and even in petroleum, I mean, giant company like Shell and Total and Santos in Australia use it as a process of prediction and process development. So they mentioned that they built 27% fewer prototype by using the simulation, and they shortened the length of the development by 29%, which is a great number. So basically, by using the modeling and simulation technique, you can design a better product or optimize the performance and reduce the development cost and get the product to the market faster, which we cover most of these points in this seminar. So simulation concept can be applied to many processes. But in this seminar specifically, we focus only on application of simulation in fluid dynamics and fluid flow. So to start, we need to take a closer look to the definition and some example of fluid flow. So fluid dynamics is a subdiscipline of fluid mechanics that describe the flow of fluid like liquid and gas. So fluid dynamics has a wide range of application, including calculating forces and moment on aircraft, or determining the mass flow rate of petroleum through a pipeline, or even predicting the weather pattern, or understanding the flow of blood and cell in a vein, or modeling a chemical product in chemical reactor. Fluids flow encounter in every day of our life, and I can say almost every engineering problem includes the flow of both fluid and heat. So if you are a meteorologist interested to study some phenomena like movement of hurricane, or the effect of the flood, or effect of the fires in forest, or rain, or impact of the wind in a building, or if you are an environmental scientist concerned about air pollution and transport of contamination in river or ocean, or even if you're a civil engineer working on the HVAC system, want to test if the fan working properly in a room, or air conditioning is cooling or warming enough for a building, or if you are a biologist involved in a study the flow of blood in a vein, find the breathing pad inside the lung, or find the drinking pad inside the body, you can use this instrument. So for bulk of you who is chemical engineers, as I do, that would like to study the chemical reaction and see the efficiency of a fuel in a furnace, or even design a new heat exchanger or something like that, you will certainly get the power from the simulation. So this is the outline of my presentations today. I briefly mentioned the simulation benefits, but you will see some case study with the simulation role highlighted in a coming slide. Then I explained the process of the simulation, a bit of theory. We won't deep go through the theory because it's not the interest of our seminar today. I need to mention that it's multidisciplinary and cross different disciplines like physics, biology, and etc. So for performing a proper simulation, you need to be competent at fluid mechanics, physics, mathematics, geometry, computer coding, programming, algorithm, and so on. And we compare the simulation with experiment, just in case that we know what's the difference between these two. We finish our seminar with a couple of case studies that I'm going to explain about them soon. So the simulation concept, in principle, can be applied to all transfer phenomena. So transfer phenomena, as its name suggests, is the movement of various entities such as mass, momentum, energy through a medium that can be fluid or solid. So as an example, a transfer phenomena can be heat conduction. which is the transfer of energy, or fluid flow, which is the transfer of moment, or molecular diffusion, which is the transfer of mass, or radiation, or electrical charge, which is the transfer of electricities in semiconductor. So transfer phenomena can be described by set of partial differential equation. CFD, which stands for Computational Fluid Dynamics Simulation, by definition is the art of replacing such system of partial differential equation by a system of algebraic equation that can be solved by digital computer. So the solution to a fluid dynamics problem typically involve the calculation of various properties such as flow velocity, pressure, density, temperature in a function of space and time. This is process of simulation. So what I've done here is to categorize process of simulation in 3 different steps. So pre-processing means that you need to understand the geometry of your case. So probably what we need to run a simulation is a CAD file because it can define the geometry. Then we need to statement the problem and understand what's going on through the system. And then we need to convert the statement of the problem to the mathematical model. And in the next step, we have to convert the geometry into a mesh, which you will find in the next slide. What is the mesh? It means that we discretize the problem into a space and a time. So in a processing, what we need is a computer. So cognitive solving model, we need to run the simulation. It can be run either on your personal computer or a cluster. So if the problem is big, the number of the equation is a lot, so you need to use the cloud computing system. We've been using Amazon Web Service in our project. We use Rescale, which is a HPC system based in US. We used to use eResearch SA in South Australia, but it's closed. In UniSA, just recently, they announced that the HPC can be accessible for all researchers and students and staff. They call it Tango 2, which is promising. So in some case, we can use this platform too. In post-processing, it's only about the analyzing of the data. So we can visualize the data and validate the result if it's required. This is the breakdown of a simulation process I discussed in a previous slide. So this is a very simple example of a flow around a cylindrical post in a 2D. The CAD file that's an input to the process looks like this. If I can, looks like this, which define the input and output through the system. This slide shows you the discretization, the discretization of the domain mesh that define the geometry and the flow domain of the interest. So what we've done here is to divide the geometry into very, very small piece of mesh. And then this is the set of the equation that's normally needs to be solved in this domain. Because of the format of this formula, we call it partial differential equation, but don't be scared of the math because I won't go through the detail of this equation. The partial differential equation then needs to be converted into algebraic equation, and then we can find a parameter that we are interested to find in one of these mesh. And then by applying the appropriate boundary and initial condition to the whole domain, we can find the quantity of the interest in the whole domain and integrate the result into the geometry. You will find the distribution of the quantity at every point in a space and a time within domain. So the quantities such as velocity, pressure, turbulency, and temperature can be solved by this method. And as you can see in top of this slide, it's a velocity field. Personally, I really like this slide because you may have this question at the back of your head saying that why should we bother ourselves when experiment is also available? So with the experiment, you'll find the description of a phenomena by measurements. But with the simulation, you'll find the prediction of a phenomena by a computer. So in each experiment, you can measure one quantity. For example, you can measure the temperature or concentration, but with the simulation, you can define all the required parameter in the background of the simulation and find the result by solving the equation. With the experiment, you have less maneuverability because at the time you have a limited number that you can measure, but with the simulation you will have the history of the parameter. For example, you will find the history of the temperature in different time and different point. When you jump into the laboratory, you need to work your case in laboratory scale, but with the simulation you can re-scale it easily and do the actual fluid domain. And there are a limited number of the problem that can't be solved by simulation. So you will have this flexibility to do whatever you want and do as much as imaginary and crazy idea in your design as possible, and then test it without doing experiments. This slide shows as a snapshot of couple of projects we've done on a simulation of fluid flow in a microfluidic system. It covers a wide range of application from mineral processing to solvent extraction, lab on a chip, cell therapy, and biosensor for early detection of the cancer. In following a slide, through 4 case studies, I'm going to demonstrate the application of fluid dynamic simulation in design and operation of microfluidic system. So the case study have been very the benefit of having the simulation capability on board as an integral part of the design and manufacturing process. So at the first case study, you will see how simulation can help you to discover the better design faster and get the right product to the market faster. Some companies still use physical prototype to validate and correct product design. Physical prototype can be costly, and large stage issue can be even more costly to correct. One of the main advantage of simulation is that they are able to provide user with the prediction of the future when the real design is made. This allows the designer to determine the correctness and efficiency of a design before the design is actually built. So instead of using the traditional design method of hypothesis by experiment, followed by experiment, or guess and check, we will use the design with simulation to avoid the loop of design, build, and iteration. At the second case study, we will show how to optimize the performance of a device by simulation. The third case study, we will point out the role of the simulation to understand the dynamics of fluid and complicated geometry. And in the last case study, it's going to be revealed how we can expand the new device development behind jumping into the lab. So it's the first case study. In this case, I'm going to discuss the detail about designing a microfluidic slurry handling platform for ion sensing to highlight the benefit of using simulation-driven design and to save time and iteration. So it was a joint collaboration research project between Future Industry Institute, University of South Australia, and University of Tasmania, Central South University in China. And we had Megato, which is a mining company, was on board with us as an industrial partner. This is a multi-layer glass device. So let me change it to laser pointer. Here we go. So this is a multi-layer glass device. It's made up of 4 layers of glass. It's very expensive to build. For each, you need to expend $1,000 to fabricate this device. And the fabrication process is complex and lengthy. So this table shows you the fabrication process and the time that each process could take. So to build one of these microchannel, you need to spend 21 days. And you need to spend another 2 days to test it in laboratory. So fabrication plus testing time is 23 days. But with the simulation, we can minimize it to 1.5 day of design and analysis, which I'm going to show within a couple of seconds. So if you do the math, we built 75% fewer prototype we save $8,000 in fabrication process only, and we shorten the development time by 60%. As an introduction to this project, this is a mineral processing flow diagram for extraction of the metal. So if you find a valuable ore in a mine site, the first step is to crush it and mine the ore. In mineral processing, flotation used to separate and concentrate ores by changing their surface to be a hydrophobic or hydrophilic condition. So the surface are either repelled or attracted by water. It's very important process that separate the hydrophobic valuable mineral from the hydrophilic waste gangue. So online and continuous ion monitoring in complex flotation system is very important because it will aid a better understanding and control of the process. It increases the yield and it minimizes the cost and environmental pollution. So the major challenge in direct sampling are the slurry sample has a high solid loading. It's near 40% solid loading, but we need to sample the ions only. And to sample from a turbulent suspension, turbulency exists in a slurry phase and the condition change quite rapidly. So the key here is to be able to collect a small volume of a fluid free of particulate matter from a stream with a high solid loading. These can be difficult for a point in a process line that contain a high solid loading, which can damage or even break and block the current array of real sensor. So this is the flotation system we'll focus on in the next slide. As you can see here, it's very complex. There is different particle size in it, and the condition in this stage is very turbulent. To address this challenge, we propose this we propose the microfluidics slurry handling platform, as you can see here. So the left-hand side image, which is a schematic, the experimental setup used for the extraction of iron from metal. The samples was placed in a beaker and stirred at the required speed using an impeller. The microfluidic device, as you will see here, was immersed below the solution surface, while the fluid connection, which are here, connected were kept above the solution. So two syringe pump were connected to the inlet and outlet, and the absorbance measurements were done across the Z cell, which with a quartz window. As you can see in the middle figure, we presented a new microfluidic device that interfaced the laminar flow in a microchannel with a complex slurry sample under turbulent condition outside through a single slit, which we call it diffusion window. Diffusion window is designed for extracting a small ion, but not particle under turbulent condition. But how does it work? These figures show the detail of what's happening within the diffusion window. So basically, the ion, because ion moves faster than the particle, diffuse in diffusion window, and there is a laminar flow coming through the diffusion window, taking the ion with itself toward the sensor, and a Z cell will measure the ions in the right time and position. So I mentioned before, the device is a 4-layer glass chip. We could potentially fabricate the chip with 10, 25, 50, 100, and above micrometer depth for diffusion window. So the main question is that what is the right slit depth for diffusion window in order to break the turbulency? We performed simulation for all 4 assumed depths in parallel. So the simulation results at the right side here, showing the extent of turbulency for 50 and 25 micrometer deep extraction window. As you can see, for 25 depth extraction window, the turbulency break at the 600 micrometer from the slit opening. So simulation used to predict the shielding effect of the slit against the external turbulency and find the point at which we can break the turbulency and stop the turbulency penetrate through the diffusion window. This is the slurry taster chip that fabricated and tested successfully by using simulation-driven design. Once we've built the model of the device, we can use the other capacity of the simulation to analyze it and adjust one of the important operational condition, which is flow rate. As you can see in these two velocity streamline, we have done different simulation with equal flow rate and flow rate with offset to visualize the flow in diffusion window and see its effect on the flow regime. Also, these results show the proof of concept for the device, and at the same time reveal why direct sampling doesn't work. Because if you look at the streamline, you will see the direct sampling actually doesn't work because the fluid has to come from the outside. So particles are drawn into the device. When you add an input flow, something like we did, this gets pushed out of the slit, which theoretically stop the particle from going in, but the fluid is still free to enter to the chip. So we could map out the velocity and pressure profile at the opening of the slit, which was very important for us because we use it to do the further analysis and calculate the slurry flow rate and find the efficiency of the device. So to wrap up this case study, in this case study, the chip was fabricated based on a simulation-driven design. The simulation was used for visualization, and the simulation helped to tune the inlet and outlet flow rate of the system. So the second case study is pretty much in the same mineral processing. So it's about solvent extraction in mineral processing, which was done by the grant we could receive from the federal government. And we had fortune to have Anglo-American and Johnson Matthey on board with us as an industrial partner. So you're already familiar with the mineral processing plan, but for this project, we focused on a solvent extraction for metals. So now the question is that, what is solvent extraction? After leaching, solvent extraction using various extractants is often used to separate and purify the individual metals, such as rare earth element metals. So this schematic figure shows an example of separation of dysprosium from an aqueous phase containing the other metals, such as lithium and other impurities, by contacting the aqueous phase to an organic extractant phase. As you can see in this figure, over a period of the time, the solvent extraction has happened and an organic phase enriched with the desired metal. The bulk solvent extraction method is common. It employs a mixer settler. The aqueous and organic phase are combined and vigorously stirred to form an emulsion. At equilibrium, mixing would stop, and two phases are separated by coalescence based on the difference in the density of two phases. Bulk solvent extraction is efficient for extraction of system including mineral material, but for rare earth element, it's required to have hundreds of units for extraction, scrubbing, and stripping, and resulting the rare earth element refineries to be a very big portion of the factory with a long processing time. On the other side, solvent extraction of rare earth elements can be carried out in a microchip using co-flowing stream of immiscible liquid, because it gives you a high surface to volume ratio. You can control the surface to volume very precisely. You can save solvent, and you can use less amount of solvent in this process. It's fast, it's cheap, it's clean. But the main challenge is to how scale up the volumetric throughput of a microfluidic device. This extraction have been demonstrated on a smaller scale, but we design a microfluidic chip for high throughput application. You can see this chip in the top left of this slide. It's made up with glass, and it has 32 micrometer thickness. This figure shows the stream aqueous and organic stream entering the high throughput solvent extraction chip. This chip creates 24 aqueous and 25 organic alternating stream merging to each other in a contact zone, which is here. And this is the place that the extraction takes place. The figure at the top, I mean, here is which I point with the mouse, shows the view of contact zone from the top. All the stream entering to contact zone side by side, as you can see, and find their way toward the outlet. The bottom figure here is the side view of the contact zone, where the aqueous stream is shown with blue and organic stream is shown with red. So the position of interface and the width of each stream can be controlled by tuning the flow rate. For having streams contacting each other properly without any breakup or producing any droplet, we need to know the flow rate of each streams. This challenge was answered by simulation. So we consider the contact zone and run multiple simulations with different aqueous and organic flow rate and find the width of each stream in each section of the zone. So these are the contour of volume fraction of the aqueous and organic phase at the beginning. This is at the middle and close to the outlet of the contact zone. By having these, you can find the velocity profile at the interface of these two phases. And you can see here an organic stream is confined with the two aqueous stream at the top and the bottom. But this chart is the main outcome of the simulation in this project. It shows the width of organic and aqueous phase in various flow rate ratios. For example, if the flow ratio is chosen to be something like 2, then you would expect to have 200 micrometer width of organic and around 100 or probably less than 100 width of aqueous phase. This chart can be attached with the chip as a reference to find the best operational condition. One of the advantages of simulation we mentioned early in this seminar is that you can monitor the evolution of your desired parameter in a course of simulation and have all point of the result in all time. Just an example here, we can monitor the development of the flow from the injection time until reaching to the steady state condition. And here it is. This is the high throughput solvent extraction chip, well fabricated. To summarize this case study, the simulation helped here to accelerate the commissioning of the device by providing reference to find the best operational condition of solvent extraction chip. It was well used to visualize the fluids interface and find the surface area between two phases, calculate the mass transfer, and estimate the efficiency of the device. For the next case study, I need to grab your attention from mineral processing application to a completely different field, which is biological application. I hope you like it. So this case study is about our collaboration with Indie Lab, which is a startup company in the US. Their vision is to develop a scalable hardware for gene delivery to treat patients with advanced disease like cancer with microfluidics vortex shedding. In very simple and a mature word, CAR T-cell therapy is a subdiscipline of gene-modified cell therapy. So this is a way of modifying the patient's own immune cell, which are T-cell. I mean, the T-cell are responsible for immune cell, we know that, to simulate them in order to attack the cancer cells inside the body of the patient. So CAR T therapy is made by drawing blood from patient, then as you can see and you can follow in this diagram, drawing blood from patient, then separate out the specific T cells. In the third stage, then modify them with a gene construct. So it can be an engineered construct or engineered virus or something like that. And then infuse the T cell back to the body of the patient. In gene delivery step, the construct delivers genetic material to the cell and modify the cell such as they can attack the cancer cell. So it's more about improving and boost up the immunity of a patient's body. So vortex shedding is an oscillating flow take place when a fluid pass a bluff body such as post at a very certain condition. So there are 5 steps involved in this device. The first step, cells are mixed with the gene construct. The second step, the flow through posts create the vortices. In the third step, vortices disrupt cell membrane. In a fourth step, the gene are delivered into cell, and in the last step, cell repair itself. So cell are mixed in a suspension with desired construct, then exposed to a hydrodynamic condition and fluid force perforate the cell membrane. So the microfluidics vortex shading here is used to gently and temporarily open the hole in a cell membrane without affecting the cell viability and deliver the genetic material directly to the cell. This is the microfluidics design for this purpose. The design is very complex. You can compare the size of chip here with an Australian 5-cent coin, which you can see it's probably half of 5-cent Australian coin. Here is more zoom in of the design with SEM image of the feature. It was designed in order to have a section with a channel at the beginning to conduct the cell with gene construct to the pillar, which you can see in the middle of this micro channel. And this is the place that the vortex shading takes place also. And another section at the end to conduct the cell with the medium toward the outlet of the channel. The first step in this project was proof of concept. For this purpose, one post is considered for simulation, as you can see here, the initial stage of shading formation, the formation of von Karman's vortex street, and finally the development of the vortex shading we could capture successfully by simulation. These are the velocity vectors colored by the order of magnitude. So hot color represent high velocity region and cold color represent low velocity. And this is the dynamic of vortex shading. This is a microfluidics vortex shading. It's very, very unique. The vortex shading formation behind a cylindrical post in this chip can be obvious by doing the simulation. The flow is fluctuation along the both side and a drag and lift force acting on a post. So the result in vortex shading can be frequently observed, and it's kind of the repeating process over the time. In the next step, what we've done is a column of posts is considered to simulate the evolution of the microfluidics vortex shading and model the interaction of different shading on another and the surrounding world. As you can see, the combination of vortex shading gives you a completely different environment, so it's required to study with more detail. And in the last step, this is a device scale simulation, which you can see what's happening from the time we inject the liquid inside the microfluidics to the time that flow become completely fully developed. I need to highlight that this device is working under high pressure, and the Reynolds number inside the device is really crazy. It's something like 260, which you couldn't imagine we have this pressure and velocity inside the microfluidic device. If you pay attention to order of magnitude of the velocity here in the bottom of the animation, you can see it. I mean, the velocity in a high velocity region is something like a 10 meter per second. And you will see that it's experimentally impossible to study these phenomena in this chip. And the simulation, we believe, is the only option to capture these phenomena inside the microfluidic device. Simulation at this stage allows us to answer a lot of questions. For example, the first question, how long does it take for the flow condition to be fully developed? We can monitor the lift convergency over one post or column of the post. So the variation, as you can see in this figure, shows a sinusoidal pattern that is a sign of sustained vortex shading process in a microchannel when Karman's streak is formed, which I explained in a previous slide. So the next question is that, can we use this simulation to optimize the device? The answer is yes. So probably at a specific inlet pressure, which we could capture during the simulation, a huge pressure drop happened at the beginning due to the recirculation happened at the top corner and the bottom corner of the device. So we can use this result to optimize it and said that instead of having this angle, let's make it like a meniscus, or like make it like a nice curvature. And the last question is that, are the cell being processed in a uniform manner? So we can find the cell trajectory here and analyze the speed of the cell and dynamic force and shear stress imposed on a cell during this journey. This is the trace of one particle, but we extended the simulation to understand the dynamic of a particle and dynamic of the cell in this device. So we represent the cell with a hard sphere, but it's always possible to make your simulation close to the reality, because the actual shape of a cell is not like a hard sphere, it's like a donut shape. So with a donut shape, we need to consider different strategy to represent the cell, which you can see it's a kind of meshed cell instead of considering the cell as a hard sphere. This is the last slide for this case study. By applying vortex identification method, we could point out not only the position of vortices, but also we could find the order of magnitude. This is a contour of microfluidic vortex shading in a chip. Vortices are created at the back of the post, which you can see in this snapshot, and detach periodically from either side of the post. And the color bar at top showed the strength of each. So the simulation in this project paved the way for us to model the experimentally inaccessible condition, and also allow us to check this variable for different design idea in a manner that's not available through the experimentation. This is the last case study. I will review it very quickly. In this case study, we're interested to know the hydrodynamic focusing in a microchannel. Hydrodynamic focusing is a technique basically relying on squeezing one of the stream in a 4 microchannel intersection by 2 side stream and reshape it downstream into a thin film. So it's usually focusing of a liquid flow by second immiscible less viscous liquid flow. It has several application in microfluidics, such as microcapsulation, microreactor, and lab on a chip, which can use lab on a chip use this phenomena a lot. But the fluid's property, such as flow rate ratio and viscosity ratio, or even the focusing geometry like width and inlet angle of the stream, have direct effect on the shape and size of the focus stream. This device specifically was designed for flow focusing microcapsulation to encapsulate a living cell to protect them in a safe environment and avoid any cell damage and rupture. So the designer at that stage hoped to produce a microfluidic device with this technique to make a shell of encapsulating fluid, cover the cell, and isolate it from ambient temperature. But as I explained, you can consider the variety of configuration either in a term of the fluids dynamic or either in a term of the focusing environment to produce different kind of the structure. So the top row shows you the effect of the viscosity. This is the hydrodynamic focusing result if we use high viscosity ratio for both fluids. This is the medium range and this is the low range. Even if you change the width ratio of this cross intersection, you will see different structure and different shape for the droplet that produce after this intersection. And by changing the inlet angle, you will see even a different structure. This is the 45, this is 90, and this is 135 degree. So it's very dynamic, and you need to decide which of these structure best suits for your work and for your study. This flow regime map is the outcome of the simulation. So the capillary number represents the relative effect of viscous drag force versus surface tension force acting across an interface of two immiscible liquid, as I'm pretty sure you know. For example, if you choose the both liquid to have high capillary number, you will end up with a trading flow. But if you choose both of liquid to have the moderate capillary number, you will end up having a kind of the jetting flow. And if you keep the capillary of the second liquid, but even decrease the capillary of the first liquid, it produces dripping flow. And by having the low capillary number for both liquid number 1 and liquid number 2, you will end up to have the tubing flow. And even further, if you increase the capillary of the first liquid, it's a displacement and a fingering flow. And the variety of configuration you can find by this configuration. We are reaching almost at the end of the seminar. I just wanted to highlight that having a theory and a simulation study done with a scientific project will increase the chance of work getting published and promoted in a reputable journal in the field. So our cell therapy simulation effort was featured by Alliance of Advanced Biomedical Engineering and American Society of Mechanical Engineering, and being archived in BioShiv and published in Nature Scientific Report. So the simulation finding of most of our other projects alongside with experimental results have been published in reputable journals such as Microfluidics, Nanofluidics, Angewandtechemie, the Journal of Colloid Interface Science, Chemical Engineering Science, Biomaterial, and Methodics. And also, we could deliver our simulation results with the experiment to the national and international conference like ANFF in Australia and New Zealand and Microtest in Switzerland last year. This is the logo of our current collaborators. We continue our collaboration with Future Industry Institute at University of South Australia and Charles Penkin Center and Hart Research Center and University of Sydney. We just started the project with Australian Synchrotron and a scientist in Flinders University. And another project, we are trying to find the way to run it with the CSIRO and University of and UNSW in Sydney, and another project with Monash University in Melbourne. The simulation played a great role in microengineering winter school last year. Each year in the University of South Australia and Australian National Fabrication Facility SA node, we run microengineering winter school. So it's a combination of all beautiful stuff. There is insight session, there would be lecture, there would be practical session, and you will have this opportunity to do the experiment in our world-class clean room facility. You will be introduced to design and fabrication of microfluidics device, electronic device, MEMS, optical, and sensing stuff. So if you are interested to be involved, it's going to be in July, hopefully this year, and you can just check our website or contact us to give you more information. This is the conclusion. Sorry if it was too long. In this seminar, we briefly discussed how leveraging your product simulation twin instead of physical prototyping can maximize the value of your design asset and reduce the cost of innovation and streamline your process from engineering up to the manufacturing. You can use the simulation to design a better product, optimize it, optimize the performance, reduce the development costs, get your product to the market faster. You can understand the dynamic of a fluid in complicated geometry, model in accessible condition, and expand the scope of development of the new device beyond going to the lab. This is my favorite photo. This photo is an outcome of a fluid dynamic simulation, shows the magnitude of the velocity around a micro-sized cylindrical post in microfluidic device when the regime is changed from laminar to turbulent. As this looks like the wings of a butterfly, we have called this a snapshot as a butterfly in microchannel. This photo has been won the People's Choice Award for Image of Research competition at UniSA at 2018. Thank you very much to attend to the webinar. I would like to open the discussion to you and ask you, what can serious CFD simulation do for you? Thank you.
Okay, thank you so much, Moein, for that. That's brief and very exciting trip through some of the projects that you've done up to this point. I would like to give you a round of applause, and I'm sure everybody else is going to do it with me, but thank you.
Thank you.
We do have time for questions. So as I described a little earlier, if you wish to ask a question, please raise your hand at the bottom of your screen and I will unmute your microphone and allow you to speak and ask Moein your question directly. While people are putting up their hands, Moein, what is the requirement for any person who wants to come in and do a simulation? What do they need to bring with them to have a conversation with you?
Firstly, what I need to know is about the detail of their research and their project. Can you hear me?
Moein.
Can you hear me?
No? Hold on. Sorry.
Hello? Hello?
Try that again?
Can you hear me, Jane? Jane? So Jane, can you hear me?
Yes, we can now.
Okay, yeah. So sorry. The first thing we need to know is the detail of your study. So I need to fully aware of what's going on in your device and get myself familiarized with what is the process, what is the main reason you want to make the device. Is it a heat transfer? Is it a mass transfer? Is it a turbulency? Is it, I mean, the context is very important. So this is the first thing. The other thing, we need the collaborator to bring with their self for the simulation is the CAD file. So with the CAD file, we can review and understand the input and output and the mechanism and this sort of the stuff. So having two sentences or 3 sentences about the device and the CAD file will help me a lot, and this would be the initial stage of starting a conversation and considering to see if the simulation is applicable in their case or not.
So Kirill, can I ask you to ask a question?
Hey there, can you hear me?
Yes, we can.
Awesome. So my name is Kirill and I'm an engineer for the working for Leica Biosystems. I just had a question looking at the case studies you did. Is there a sort of much higher difficulty in simulating like a liquid to air interface?
Thank Kirill for your question. Can you explain more about the application of injecting a liquid into air?
Yeah, so in sort of high level terms, we have a chamber surrounded on all sides with a polycarbonate surface, and then we're injecting different reagents in. So the chamber is empty when the fluid comes in, and then we are interested in getting a really even flow front in that application.
So it's really doable, but we need to consider how many particles do you want to study at one time. If it's a one droplet or it's a couple of droplets, it's absolutely doable, and we've done a couple of projects like that before. But if you have a unlimited number of the liquid particle you want to inject in a chamber, we need to consider the interaction of the liquid to liquid instead of liquid to air, which increase the complexity of the simulation. But as long as we need to work on the limited number of the droplet, and the environment is not infinitive, it's the boundary is limited, we can definitely help you to find the distribution of the particle inside your chamber. There isn't any problem with that. And about the simulation time, it really depends on the size of your geometry. If it's in a micro scale, that's doable within a day or two. If it's in a bigger scale, we need to run your simulation in parallel. But the answer briefly is yes, and this would be an interesting project.
Okay, awesome. Thanks a lot.
Yeah, no worries, Karen.
So are there any other questions out there?
Hi,
Ishan? You're able to speak.
Hello, my name is Ehsan. I'm from RMIT University in Melbourne. I'm a postdoc. Just had a question, Moein, for you regarding your simulation of slurry. As far as I know, slurry is the Herschel-Balke fluid. Have you actually simulated this fluid as a Herschel-Balke fluid, or you just assume it's a non-Newtonian fluid? And what's the like a coding program that you use?
Hi, Ehsan, and thanks for your question about the slurry. We done the simulation based on the need of our industrial partner. So our industrial partner was interested to see if they get a very small sample of the slurry and do the test and get the parameter that he wants, what's the structure of the microfluidic would be. So with a small scale of the slurry, we assume that it's Newtonian flow. So we haven't included the non-Newtonian, but it doesn't mean that we can't do this. We couldn't do this, we didn't do this because the main interest at that simulation was letting the ion penetrate through the diffusion window and sensing, but not the particle. So the condition of the slurry was not very obvious for us and was not very subjective to our study. What we've done is make beaker size slurry, put the particle size with a different distribution, and also introduce the ion and see what is the reaction of the device that's wanted to build in this scale. So to answer your question briefly, the model was based on the Newtonian, not Newtonian, and the interest was to study the behavior of the ion, not the particle. So does it make sense?
Yep. Thanks for the clarification.
Yeah, no worries, that's fine. So if you have more questions, we can keep in contact, and I'm happy to answer all the questions.
Thank you for those. Are there any more burning questions? Wonderful. In that so sorry, I'm getting my instructions here as to what I have to say to finish this seminar off. I'd like to thank Moein for putting this presentation together and being very clear about what the benefits of simulation are and what we can do for people who are out there trying to model what's happening inside the devices. I'd like to thank Tom Edishaw, who has set this up and made sure that our webinar is actually working and that we've actually been able to talk to you all today, which is no mean feat, I have to assure you of that. If you need to contact us or contact Moein, his contact details are on our website, anff.org.au. You can also contact ANFF HQ directly and we can put you in contact. And if you have any questions about ANFF in general, please do contact us. You'll find my contact details on the website, Tom's contact details on the website, and Moein's contact details are right in front of you at this moment in time. To ensure that this service starts getting some usage and that we can actually build it into a larger and better service going forward, we are offering discounts on our regular access fees to get this up and running. So if you do have a project that you would like or that you would like to try out, please contact us. The fees that you will pay will be lower than normal, and you may get a quick publication out of it, or even reduce the time it takes you to get a real device up and working. So please feel free to contact us if you do have a possible project. As always, I'd like to thank everyone for turning up today. If you have any questions or you want to contact us, please do so. And with that, I will say thank you and stay safe, everybody. Goodbye.
Thank you very much.